Did you know that in 1965, the United States launched an experimental satellite powered by a fully functional nuclear reactor? It worked like a charm for 43 days before a little malfunction shut it down. But here's the truly wild part. It's still up there, silently circling our planet every 112 minutes.
So we're going to dive into the incredible story of this atomic satellite. And we're not going to do it with speculation. Nope. We're going straight to the source, the original, now declassified engineering documents that spelled out its design, its mission, and, well, its ultimate fate.
To really understand how a nuclear reactor ended up in orbit in the first place, our story actually has to start right here on the ground. We're winding the clock back to the 1950s, the absolute peak of the Cold War, and we're looking at a company that was on the bleeding edge of the new atomic age.
And that company was Atomics International. From their facility out in Van Nuys, California, their whole mission was to explore the peaceful side of nuclear power. You could say this was the proving ground, the spot where all the foundational research and hands-on experience paved the way for one of the most ambitious nuclear projects in history.
And listen, these folks weren't just drawing on chalkboards. Before they could even dream of going to space, they built and operated these two small-scale research reactors right there in California. The documents show the L-47 produced just 5 watts of power, the L-77 a whopping 10 watts. Now, that sounds tiny, right? But it was never about the power. It was about getting that crucial, real-world experience you need to build a reactor that could actually survive the chaos of space.
All right, so with that expertise locked down on the ground, the stage was officially set for the star of our show, the SNAP-10A reactor. And because we have the original design memos, we can basically deconstruct this incredible piece of engineering, layer by layer.
Okay, so the heart of any reactor is its fuel, right? For SNAP-10A, the engineers went with a solid alloy of uranium zirconium hydride. And this was absolutely critical. I mean, think about the unforgiving environment of space. A liquid or gas fuel would be way too complicated and risky. This solid-state fuel, though, it was designed to be tough and predictable, which is exactly what you want for a mission that's unmanned and thousands of miles away.
And all these different parts had to work together in perfect harmony. The fuel was held in a stainless steel core vessel. Wrapped around that was a beryllium sleeve, which acted as a reflector to bounce neutrons back into the core and keep the reaction going. The control system was brilliant, just 4 rotating drums also made of beryllium. And then finally, a lithium hydride shield was there to protect the satellite's delicate electronics from all that radiation. It was really a marvel of compact, super efficient design.
So just how compact are we talking? The entire assembly, the reactor, the core, the vessel, all of it, weighed only 250 pounds. That's it. That's less than a lot of people weigh. When you remember that every single ounce costs an absolute fortune to launch into orbit, you realize this thing was a masterpiece of careful, clever engineering.
So building the reactor was one massive challenge, but turning it on remotely while it's tumbling through the vacuum of space thousands of miles from home, well, as the design files show, that was a whole other level of hard.
This quote, pulled straight from an old engineering memo, really gives you a sense of the incredible patience this thing required. This wasn't like flipping a light switch. The startup was a slow, deliberate, totally automated process that was designed to be as stable and foolproof as possible. From the second the command was sent, it was going to take a full 9 hours for the reactor to be up and running.
And here's exactly how that careful sequence played out. Once the go command was received from Earth, the course control drums would snap into place, getting the reactor right to the edge of a chain reaction. Then the fine control drums began this slow, methodical dance, stepping in just half a degree every 150 seconds. After about 7 hours of this painstaking tuning, the reactor would finally achieve criticality. 2 hours after that, it would hit its full operating temperature, ready to start making power.
Of course, when you're putting nuclear power in space, you absolutely have to plan for the worst-case scenario. And the engineers at Atomics International spent a ton of time meticulously planning for what should happen if something went very, very wrong.
Yeah, this is the big one. It's the most important question you could possibly ask. What happens if the satellite fails and starts falling back to Earth? Well, the declassified documents show they had a multi-layered, really thought-out plan for that exact scenario.
Their main shutdown system was, well, it was both elegant and brutally effective. 3 different redundant signals could kick off a termination sequence. A 1-hour timer would start, giving ground control a chance to grab some data.
Then a tiny electric heater would melt a special metal alloy holding a retainer band together. The second that band broke, powerful springs would physically shoot the two halves of the beryllium reflector away from the core, permanently stopping the chain reaction. Dead.
But what if it actually came down? The plan for that was just as thorough. All their reentry analysis predicted that the intense heat and friction of hitting the atmosphere would cause the reactor to break apart, and the individual fuel elements would completely ablate, just burn up, at an altitude way up there, above 220,000 feet, safely dispersing the material in the upper atmosphere.
So after 43 days in orbit, a simple voltage regulator on the satellite failed, which triggered that automatic shutdown we just talked about. And ever since then, SNAP-10A has been silent. But its story leaves behind this dual legacy, one that's still going on in orbit, and one that ended a long, long time ago right here on Earth.
This is where we start getting into the concept of deep time, which is just mind-bending. See, even though the reactor is shut down, the fuel inside is still decaying, and that produces a tiny amount of heat. When it launched, it produced 500 watts of electrical power. But the original engineers calculated that even 2,000 years from now, it will still be putting out about 48 watts of thermal heat. It's a technological ghost, still warm after millennia. And this brings us to a fascinating contrast. While the satellite itself is on this multi-thousand-year journey through space, its birthplace here on Earth has vanished. The Van Woen facility, where this whole story started, was decommissioned, and all radiological activities there stopped way back in 1960.
And the Earthbound part of the story has a very definitive ending. Decades later, in 1995, the U.S. Nuclear Regulatory Commission went and inspected the old Van Allen site. Their report was conclusive and clear. The area was totally clean. It says, and I quote, "No readings above background were identified in or around the former reactor room." That confirms the cleanup was a complete success and the site was safe.
So, we're left with this. SNAP-10A was a huge technological triumph, no doubt, but it's also a permanent artifact, a ghost in the machine of our solar system. And it forces us to ask a really profound question. As we create new technologies, whether they're in space or online or even inside our own DNA, things that have the potential to last for thousands of years, what's our responsibility to the future? How do we plan for a legacy that will long outlive every single one of us?